Welcome to G Fun Facts Online. Think about your smartphone. It's a window to a virtual world, a hub for connection, a tool for work and play. It feels almost weightless, ethereal, but the digital age, for all its virtuality, is profoundly physical. It's built from the very crust of the Earth, and it's leaving a permanent mark on our planet's chemistry. Today, we're digging deep into the unseen cost of our connectivity, unearthing the geochemical footprint of the digital age. We're going on a journey from the mind to your device and back to the Earth. Every single digital device you own is like a miniature museum of geological treasures. It's a dense, intricate sandwich of elements painstakingly extracted from the ground. These are often called critical minerals because without them, our digital world simply wouldn't exist. The undisputed backbone is silicon, derived from common quartz, which forms the semiconductor wafers at the heart of every microchip. Think of copper as the circulatory system, the wiring and connectors that let electricity flow. And tin, sourced from the mineral cassiterite, is the solder that holds it all together. But the real magic and the real challenge comes from the rarer elements. You've probably heard of rare earth elements, or REEs. This group of 17 metals are the secret sauce in modern tech. They create the powerful, lightweight magnets that make your phone vibrate and your speakers work. They're also responsible for the vibrant colors on your screen. And the list goes on. The lithium and cobalt in your phone's rechargeable battery are the workhorses that keep it powered up. Cobalt, in particular, is key to its energy density and lifespan. Tantalum, often sourced from a conflict mineral called coltan, is vital for the tiny, high-performance capacitors that regulate energy flow. Gallium and germanium are essential for the high-speed data transmission that makes 5G possible. Even precious metals have a job to do. A typical smartphone contains about 7 milligrams of gold, not for decoration, but because gold's resistance to corrosion makes it perfect for coating electrical connectors, ensuring they last. This hunger for minerals isn't just about our personal gadgets. The vast infrastructure of the digital age, the sprawling data centers, the thousands of miles of communication cables, the endless racks of servers, all depend on this same suite of elements. And there's a new player increasing the demand: the green economy. An electric vehicle, for example, requires 6 times more minerals than a conventional car. Wind turbines and solar panels also need many of these same critical materials. This double whammy of demand from both the digital and green tech sectors is putting unprecedented pressure on our planet's resources. So where do these materials come from? Their journey begins with a profound and often violent act of extraction: mining. Large-scale open-pit mining, the method used for many of these minerals, fundamentally rewrites landscapes. To get to the ore, huge amounts of rock and soil, called overburden, are blasted away. This creates massive open pits and even bigger waste rock piles. The tailings ponds, which store the leftover sludge from processing, can be enormous. Some copper mines in the US have tailings ponds covering over 1,000 acres. These man-made landforms are unstable, prone to erosion and landslides, and the removal of all vegetation destroys entire ecosystems. But the visible scars are only part of the story. The real long-term damage is geochemical. When rocks that have been buried for millions of years are exposed to air and water, a dangerous chemical reaction can start. This is called acid mine drainage. Sulfide minerals in the rock react with oxygen and water to create sulfuric acid. This acid then acts like a solvent, leaching toxic heavy metals like lead, arsenic, and cadmium from the surrounding rock. This toxic brew contaminates rivers, lakes, and groundwater for miles, sometimes for centuries after a mine has closed. We see this all over the world. In southwest China, a hub for rare earth element mining, aquatic systems are heavily contaminated. Studies show that concentrations of these elements in surface water and groundwater are far above normal levels. In Spain, abandoned mine sites from decades ago continue to leach arsenic and lead into the soil and water today. The extraction of specific minerals leaves its own unique chemical signature. Take lithium, crucial for our batteries. Much of it comes from the lithium triangle in South America. Here, vast amounts of salty brine are pumped from underground aquifers and left to evaporate in huge, shallow ponds. This process consumes incredible amounts of water in an already arid region and risks contaminating the remaining fresh water with salts and chemicals. Rare earth element mining is notoriously dirty. The process often releases radioactive byproducts and heavy metals. In regions like Inner Mongolia, which is a major producer for China, decades of mining with lax environmental rules have created vast, toxic lakes and completely devastated the surrounding land. The sleek, clean device in your hand began its life in a place that looks anything but. The fact that these minerals are not spread evenly across the globe has created a new map of geopolitical power and conflict. The supply chains for many critical elements are dangerously concentrated in just a few countries. China, through decades of strategic industrial policy, has positioned itself as the dominant force. It accounts for over 60% of global rare earth production and a staggering 85% of the refining capacity. This gives them immense leverage. In 2010, the world got a wake-up call when China temporarily restricted rare earth exports to Japan during a political dispute. It was a clear signal: control the minerals, and you can control the technology. More recently, in 2023, China imposed export controls on gallium and germanium, further flexing its mineral muscle. In response, the United States and the European Union are scrambling to diversify their supply chains. Policies like the US Inflation Reduction Act and the EU Critical Raw Materials Act are designed to boost domestic mining and processing. This has kicked off a new era of resource diplomacy, with Western nations trying to build partnerships in Africa, Southeast Asia, and Latin America. But building new, non-Chinese supply chains is incredibly difficult. It can take more than a decade to bring a new mine into production, and these projects often face strong local opposition over environmental and social concerns. And China's influence goes beyond its own borders. Through its Belt and Road Initiative, Chinese companies have invested heavily in mining operations all over the world. For developing countries, this is a double-edged sword. It brings economic development, but also risks of environmental damage and long-term economic dependency. This isn't just about economics, it's about security. Many of these same minerals are essential for advanced military hardware, from guided missiles to fighter jets. This struggle to secure a stable supply is now a key part of modern geopolitical strategy. Now let's move from the ground to the cloud. The geochemical footprint of the digital age isn't just in the mines. It's also in the immense amount of energy our digital world consumes. The physical heart of the internet is the data center. These are gigantic nondescript buildings packed with servers, storage systems, and networking gear. They power everything, from your social media feed to complex scientific simulations. Running these servers 24/7, plus the massive cooling systems needed to stop them from overheating, creates a staggering energy demand. Globally, data centers are estimated to consume between 1% and 3% of all electricity generated. To put that in perspective, the energy consumed by data centers in 2022 was comparable to the entire electricity demand of France. And this demand is on a steep upward curve. The explosion of artificial intelligence and machine learning is pouring fuel on the fire. Training a single large AI model requires immense computational power. The International Energy Agency projects that electricity consumption from data centers, AI, and cryptocurrencies could double by 2026. A huge portion of this electricity still comes from burning fossil fuels, which contributes to greenhouse gas emissions and accelerates climate change. While major tech companies are investing heavily in renewable energy, the explosive growth in demand is often outstripping the supply of clean power. Even on an individual level, our devices add up. Manufacturing a single smartphone is an energy-intensive process. One estimate suggests it takes around 400 gallons of water and significant energy to produce just one iPhone. And of course, there's the daily act of charging our billions of devices. When you add up the energy used by the device, the network, and the data centers it connects to, the carbon footprint of its use phase becomes significant. So while digital tech can help optimize energy in other sectors, the digital economy itself has a massive and growing power problem. This brings us to the final and perhaps most disturbing chapter in this story, the digital graveyard. Our desire for the newest gadget, fueled by corporate strategies of planned obsolescence, has created a tidal wave of electronic waste, or e-waste. Every year, we generate over 50 million metric tons of it. That's projected to hit 74 million metric tons by 2030. The most shocking part? Less than 20% of this e-waste is formally recycled. The rest ends up in landfills or is shipped, often illegally, to developing countries in Africa and Asia. Here, it's processed in informal and incredibly hazardous conditions. In places like Agbogbloshie in Ghana, one of the world's largest e-waste dumps, workers, including children, burn piles of cables to melt the plastic and get to the copper inside. They use crude acids and hammers to break apart circuit boards to extract tiny flecks of gold. These methods release a toxic soup of chemicals into the air, soil, and water. The geochemical fallout is severe. Heavy metals like lead, mercury, and cadmium from old batteries and circuit boards leach into the ground, contaminating farmland and drinking water. Burning the plastics releases dioxins and furans, which are persistent organic pollutants that can travel long distances in the atmosphere and build up in the food chain. The human cost is devastating. People living and working in these digital graveyards suffer from high rates of respiratory illness, skin diseases, neurological damage, and cancer. Children are especially vulnerable. The World Health Organization has issued stark warnings about the risks to children and pregnant women, as exposure to these toxins can cause cognitive and developmental problems that last a lifetime. The convenience of our digital lives is directly connected to the poisoning of people and environments thousands of miles away. It's a daunting picture, but it's not hopeless. A growing awareness of these costs is driving a search for a more sustainable path. It starts with more responsible mining, so-called green mining, which aims to reduce water use, recycle waste, and properly rehabilitate land after a mine closes. But the real solution lies in fundamentally changing our relationship with electronics. We need to move from our current linear model of take, make, dispose to a circular economy. A circular economy for electronics is a system where waste is eliminated, products are built to last, and materials are kept in use for as long as possible. What does this look like in practice? First, design for longevity and repair. Companies need to make products that are durable, easy to fix, and upgradable. This would extend the life of a device and reduce the need to constantly buy new ones. Second, we need robust markets for reuse and refurbishment, making second-hand electronics a viable and attractive option. Third, we need better recycling. This means investing in innovative technologies like automated sorting using AI and robotics, and new chemical processes like bioleaching, which uses microorganisms to safely extract metals from e-waste. This leads to the idea of urban mining. Our cities are filled with discarded electronics, which are essentially rich deposits of valuable materials. 1 ton of old mobile phones can contain 300 times more gold than a ton of high-grade gold ore from a mine. We just need to get better at recovering it. Business models need to change too. What if companies leased you a phone as a service instead of selling it to you? They would then be responsible for its maintenance, upgrades, and end-of-life management. And finally, we need stronger policies like Extended Producer Responsibility, or EPR. This makes manufacturers financially and logistically responsible for the entire life cycle of their products, including their collection and recycling. This creates a powerful incentive to design products that are easier to dismantle and recycle. Building a truly circular economy won't be easy. It requires action from manufacturers, consumers, and governments. It demands a cultural shift away from our obsession with the new, towards a mindset of stewardship and responsibility. The digital age has brought us incredible benefits, but they've come at a hidden cost. The geochemical footprint of our connected lives is deep and wide, stretching from the scarred landscapes of mines to the toxic digital graveyards. But by understanding the full journey of our devices, we can start to make more conscious choices. The path forward lies in innovation, responsibility, and the simple recognition that our virtual world is, and always will be, inextricably linked to the physical one. Thanks for tuning in to G Fun Facts Online.